Hi everyone, we have here a vector v. Notice this vector notation here, this half arrowhead. The vector v can be represented in this Cartesian component form, where A is the horizontal component, B is the vertical component, and we surround these by angle brackets. That helps indicate that we have a vector. And of course, the comma here. We can represent this vector using this position vector representation, where we draw the vector from the initial point at the origin, 0, 0. That's where position vectors start. The terminal point is at the point A, B. This is the classic way to represent a vector, although we have the right to move this vector around. Now, if we are given little a and little b, if we're basically given the coordinates of this terminal point, where the initial point is at the origin, then what formulas can we derive to get r, or the length of v, the magnitude of v, and theta, the direction angle? How do we go from basically Cartesian coordinates to polar coordinates for this point, this terminal point? So if we are given a and b in red, how do we get r and theta in blue? First of all, how do we get r, or the magnitude of v, the length of v? Well, we're given two side lengths of a right triangle, and these can be signed. Remember, a and b can be negative also. We could be in a different quadrant. We could even be quadrantal. But let's say, well, here, a and b are positive. They represent sides of a right triangle, the legs. How can we get this hypotenuse? From whose theorem? You know him, Mr. Pythagoras. So from the Pythagorean theorem, which is also related to the distance formula, right, r so use blue, r, which we represent as the which we're using as a substitute also for the magnitude or length of v. Remember, you tend to use r more in calculus. R, or the length of v, is given by this, because r squared equals a squared plus b squared, right? From the classic Pythagorean theorem, r squared equals a squared plus b squared. Or if you wish, you could use more generically x squared plus y squared. But here, a and b are particular values of x and y. Don't worry too much about that distinction. All right. And to find r itself, you take the non-negative root. Again, in chapter 10, we'll let r be negative. But for right now, in this chapter, r is non-negative. We zap the plus minus. So that's going to be a formula that will get you a value for r, or the length or magnitude of v. This length here, the hypotenuse. Now, how do we get the direction angle, theta? We're interested in theta. You have b and a. You have the opposite side length and the adjacent side length. I guess signed length. They could be negative or 0. Opposite over adjacent. What trig function relates an angle, the opposite side basically, and the adjacent side? How about tangent? How can we relate theta, a and b, or x and y? Okay, well, we need tangent of theta to be b over a, or if you prefer, y over x, more generically. Bear in mind, a cannot be 0, otherwise this is undefined. But if I tell you that the tangent value is undefined, that's helpful. That means that we have maybe a 90-degree angle or a 270-degree angle. Now, I have another note here. Make sure that theta is in the correct quadrant, because you might be really tempted to say, well, if tangent of theta is b over a, can't I just say that theta is the inverse tangent of b over a? Well, that's true if b over a is positive and theta is quadrant 1. But in other cases, you better be careful. Just in general, you should be careful and make sure that theta is in the correct quadrant, especially when this thing's negative. But actually, if this thing is negative, then wait, remember the range for inverse tangent is basically from, in degree measure, from negative 90 degrees to positive 90 degrees. But wait a minute, we usually want our direction angle to be between 0 degrees and 360 degrees. So if you take the inverse tangent, if you have a quadrant 4 angle, then we actually don't want the inverse tangent because we don't want negative angles. So be very careful about using this inverse tangent notation. It's true that if the tangent value is positive, right, then we're either going to get an acute angle or 0 degrees. That's fine. But be very careful about using this inverse tangent notation. There can be some pitfalls. And also, you might end up in the wrong quadrant, as we'll see later on. So what we can say is this. We need that tangent of theta is b over a, assuming that it's defined in real, but also make sure that theta is in the correct quadrant. Okay, so pick the angle appropriately, and you have to consider quadrant issues, or maybe the angle is quadrantal. All right, so let's do some examples. Let's do an example. Example. I guess I'll, well, let's see. I'll go up here. Example. Let the vector v, remember, if you're writing it, you might want to write it like that. I'm bold-facing it here. Let the vector v be represented by angle brackets, -3, 5. So we can think of it as going from, in position vector representation, from the origin 0, 0. Whoa. Hi, what quadrant is this guy in? That's a first consideration. What quadrant is this guy in? Well, if you draw it as a position vector, right, -3, 5, that's where the terminal point is. What quadrant is that in? What quadrant is that in? -3, 5, hey, it's in quadrant 2. That's a big deal, all right? So keep that in mind. Okay, we're going to deal with the quadrant 2 angle. Okay, so if the vector is this, in component form, find the magnitude or length of v. Remember, we're thinking of that as r. And also the direction angle theta, where theta is between 0, or 0 degrees, and 360 degrees. Okay? Okay, well, some angle in here has to work, right? Pick the right one. Let's round off theta to the nearest 1/10 of a degree. So read instructions. Okay, folks, how do we go from A and B? I guess I'll put this in red. How do we go from A and B, or if you wish, X and Y, to R, or the length or magnitude of V? We use whose theorem? Mr. Pythagoras. All right. So the length of V, or R, is going to be the square root of, remember, r squared doesn't have the root. R does have the root here. The square root of a squared plus b squared, or x squared plus y squared. Right. Remember to put parentheses. The square of -3 is +9. All right. The square of 5 is 25. We have the square root of 34, which is simplified. On an exam, I might say that distances are measured in meters. Okay, like along the x and y axes, distances are measured in meters. So it might be good to put a unit like meters. Let's say these are scaled in meters. So root 34 meters, that's going to be the length of this vector, the magnitude of this vector. As far as how far you have to walk from the palm tree over here at the origin to get your tickets over here. Okay, how do you get theta, the direction angle? Well, we're going to need this formula over here, right? What relates opposite, adjacent, and the angle? Tangent. All right? Tangent of theta is b over a, or if you wish, y over x. Tangent of theta is b over a, or y over x. It's going to be the 5 over the -3. Okay? Remember that. A lot of people switch these. It's like slope, right? A lot of people switch the slope, and they turn it upside down. It's the y guy over the x guy. The y guy over the x guy, 5 over -3, which is -5/3. So the tangent value is -5/3. Okay. Now, folks, if you were to do the inverse tangent, let's think about this. If you were to do the inverse tangent, what's the range for inverse tangent? It involves what quadrants? Quadrant 4 and quadrant 1, right? This represents the range for inverse tangent. Okay, so Now, wait a minute, though. Wait a minute. What vector, as a position vector, what quadrant is our vector in? Remember? It's in quadrant 2. It's in quadrant 2. Uh-oh. So if you do inverse tangent of negative 5/3, you're going to end up in quadrant 4, and we're going to have to do something about that. So again, tangent of theta is negative 5/3. Remember to put your calculator in degree mode, because in chapter 6, we tend to deal with degree measure. Okay. The inverse tangent of negative 5/3 is negative 59.0 degrees. We can use that, but that's not our answer, because negative 59 degrees, okay, is not inside the interval here. So this is not our answer. I'll put this in red. It's not the answer. In fact, it's not even in the right quadrant. It's not even coterminal. It's not even in the right quadrant. Where is negative 59 degrees, folks? Where is that? It's in quadrant 4. All right. Here's a picture. Okay, so here's the deal. Negative 59 degrees is in quadrant 4, right? I'll put that in red. He's the wrong guy, right? So negative 59 degrees, he's over here, right? We're going in the exact opposite direction we want to go in. We want to go in the direction of quadrant 2. We want to go in this direction. Okay. So what's an easy way of getting from this direction over to this direction in terms of angles? How many degrees do we add to the negative 59 degrees to get to this correct direction over here? We add how much? We add 180 degrees. It's like a politician doing a flip-flop. We're going from here, quadrant 4, to here, quadrant 2. Here's the picture. The calculator gave you, for inverse tangent of negative 5/3, it gave you negative 59.0 degrees. You're going in the wrong direction. I mean, you want to go in this direction to get your concert tickets. You're going in the exact opposite direction. You're making things worse. You're going to have to backtrack. Okay, so how do we backtrack, right? We have to add 180 degrees. Okay, and then we get in the right direction, we get 121.0 degrees to the nearest tenth of a degree. So this packet of information should be enough. Okay, I could have said, to get to your tickets, go 3 meters west and 5 meters north. I could have given you Cartesian directions, or I could have given you polar directions. I could have said, okay, so you want to go in this direction. If you have a compass, you want to go in this direction, represented by this direction angle. You're going to go northwest in quadrant 2 from the palm tree at the origin. And you're going to walk root 34 meters. That's between 5 and 6 meters, almost 6 meters. So you might want to bring your iPhone with you. Keep track of how far you've walked. All right, so there we've gone from Cartesian to polar, basically. Going from Cartesian directions to polar directions. Next, we're going to go from polar to Cartesian.